Well, this is a red letter day in your calculus experience because this is the classic. Every calculus student since time immemorial has encountered this problem. The classic ladder sliding down the wall problem. If I have a ladder that is leaning against a wall, this is the Clark W. Griswold Christmas Vacation problem, except we'll actually change it here pretty soon. If the base of the ladder is being pulled away from the wall at a certain rate, then the top of the ladder is going to slide down the wall at a certain rate. It is not necessarily the same rate. At the very, very start, if the ladder is almost vertical, then you can pull this out 2 feet, the top will barely slide down at all. But as you get further and further away, the top begins to pick up speed. That's why when this happens naturally, that's why the ladder slams against the floor, is because the top of this ladder begins to pick up speed. And so how fast the top is sliding down depends upon where you are in this process. All right? So what we have is this. A 25-foot ladder is leaning against a wall. The bottom of the ladder is being pulled out at the rate of 3 feet per second. How fast is the top of the ladder sliding down the wall when the base is 15 feet from the wall? So that's our little problem. Well, I've drawn my picture once before. We don't really need our picture here that badly. Once you understand the basic of what's happened, this is moving out, this is moving down. So the question is this. Anytime we have a picture of this sort, the question is, what quantities are changing? What quantities are changing? What quantities never change? Well, notice the length of the ladder is not changing. The hypotenuse of that triangle is never going to change. The hypotenuse of the triangle is 25. Now you're saying, well, but you said don't put the constants into. No, this is a different notion. This is not changing. This never changes throughout the entirety of the problem. This is not a variable distance. I'm not substituting 25 in for a variable because this distance is not varying. Yes, this distance is varying. That is a variable. This distance is changing. That is a variable. I'm not going to substitute in this number or this number before the derivative because those are variables, they're changing. This value does not change. It's not a variable. It needs to be its given specific constant value. So now, these are changing, so I'm going to choose some variable letters. They can be any values you want to pick, thetas or t's or j's or whatever you want to pick. I'm going to have the horizontal be x and the vertical be y, but that's just because that's what I'm using. If you don't like x and y, you can use m and p and z and w, whatever letters you want to pick. That's wonderful. I'm going to pick x and y. And notice that nowhere in here are we given any equation to start with. Well, we'll cross that bridge here in just a bit because we need to make sure and go down our checklist. Determine what you're asked to find. What are we being asked to find? How fast is the top of the ladder sliding down the wall? We're not asked to find this height. We're asked to find how fast, what is the rate of change of the height of the top of the ladder? How fast something is changing, how fast something is moving. How fast something is moving, that's a rate of change. How fast something is increasing, that's a rate of change. How fast something is decreasing, that's a rate of change. How fast is a rate of change? We want the rate of change of the top of the ladder. We want to find, so we need to find, I want to write this down here, find the rate of change of y dy dt. And we might as well go ahead and throw in the units. Notice feet per second. So we're going to have something feet per second. All right? Now, what else are we given? We're given some more information. What are we given? We're given the 20, well, that's 25. We already have that in the picture. The bottom of the ladder is being pulled out at 3 feet per second. That means this distance is changing. That distance is changing at 3 feet per second. Is it clear? That's dx dt. So we're given, oh, my givens are over here. I'm going to write them down here. Given. We're given dx dt was given to be 3. And we're given how when the top of the ladder, when the base is 15 feet from the wall. When the base is 15 feet from the wall, we're given a specific value for x. Remember, do not substitute the variables in too soon. Now, we also need some starter equation somehow. Now, with the cone problems we were working on, I just gave you the cone problem, or the cone, the volume of a cone formula. We need some sort of a relationship. Well, it's not very hard to see. Pythagoras is happening over here. Pythagoras is happening here. So we can use Pythagoras to say, we do know we're going to start with x squared plus y squared is 25 squared. And can we note 25 squared? 25 squared, 625, that's 25 squared. So we have x squared plus y squared is 25 squared, 625. Bad looking 2. There we go. All right. Determine what you're asked to find. Got it. Got all the written stuff, written information. The given information written down. We got our starter equation. Differential count. Do we want dx dt in the problem? Yes, dx dt is given. Do we want dy dt in the problem? Yes, dy dt is what we're looking for. And so yes, differential count, we're good to go. Now we differentiate. So the differential of left-hand side, differential of the right-hand side. So the derivative here is 2x dx dt plus derivative here is 2y dy dt is equal to derivative of a constant. Derivative of a constant is 0. If you wish, you may cancel the 2's. If you don't want to, you're going to get the same answer either way. You can either cancel the 2's now or cancel them later. It doesn't matter which. So we differentiate. Ding! Substitute the givens and solve. Substitute the given information. We're given dx dt is 3. So we're given 2 times x. X is given to be 15. Dx dt is right there. That's 3. Plus 2 times, we don't have a value for y. Now dy dt is what we're looking for. But we don't have a value for y given. So you remember the rule? What happens if you need a variable that is not given? You go back where? You go back before the derivative. That's why we have this written down every time. So if you need a variable value that's not given, we need a value for y that's not given, go back before the derivative. So we need the value for y. And so we do know that, well, I'll go back before the derivative. And what do we have? X is given to be 15. Right? X is given to be 15. Y is what we're looking for. And so 15 squared is 225. Plus y squared is equal to 625. I'm going to run out of space here in just a minute if I'm not careful. So y squared is given to be 625 minus 225. Well, I can do that in my head. That's 400. And the square root of both sides of that, that's positive or negative 20. And notice we're doing a distance problem. Y is a distance. It's distance above. And so we choose y to be positive 20 because the physical nature of the problem requires it. You do not always choose positive. Sometimes you choose negative. This might be a measurement above or below sea level. If this were above or below sea level, and if we were asked to find the below sea level, we would choose the negative. You choose the positive or the negative depending upon the physical nature of the problem. We choose positive not because you always choose positive. We choose positive because the ladder height is a positive distance. So we're choosing y to be 20, and now get on with it. So I have 2 times 15 is 30, times 3 is 90, plus 40 dy dt is equal to 0, 40. And then subtract the 90, divide the 40, is that right? Subtract the 90, divide the 40. I'm going to get rid of my work over here. You can always rewind and look at it again if you need to. I'm going to steal my space back. And so dy dt is subtract the 90, divide the 40, which is negative 9/4, and that's more than sufficient. You do not need to change that. If you want to, that's fine by me. You can say negative 2.25 rather. If you prefer 2.25, that's wonderful. But as far as I'm concerned, 9/4 is wonderful. I have negative 9/4. Notice this is a negative number. This is the first time that's happened for our problem, so we want to sort of revisit that. So I want to revisit this notion of why this is a negative. Now, one thing, it's negative because that's what the algebra required. But what's happening in the problem physically must be interpreted in terms of what's working algebraically and vice versa. Anything that happens in the algebra will be interpreted somehow in the physical problem. And so algebraically, we computed a negative number. What that means is that's the rate of change that's how fast the ladder is sliding down the wall. The interpretation, and I think once you see what's happening in the problem, is pretty straightforward. Here's the wall, there's the ladder. This is moving out. This distance x is getting larger. As time goes on, x is getting bigger. This value, x, is increasing. And that's why dx dt is a positive number. But as time moves, as this moves out, this point is moving down the wall. This side is decreasing. This side is decreasing. Whenever something is decreasing, that value needs to be negative. We might be doing problems where you're filling a tank, or you might be doing problems where you're emptying a tank. If you're filling a tank, the volume of liquid is increasing. It should be a positive number. If you're emptying a tank, then the differential should be negative because it's decreasing. The quantity is getting smaller. So if something is increasing, the differential is positive. If something is decreasing, the differential is negative. That should always happen in accord with what we're getting in the equations, and it should match in accord with the physical structure of the problem. So there's our ladder pulling down the wall problem. Next, what we'll do is a variation on this theme. Our next problem is going to be, what if this ladder is retractable? And so not only is this distance changing, not only is that distance changing, but also this distance is changing. And a little more is going on, and we'll see how that works out.